Hi boys and girls, this video will comprise the lecture for section 9.3 on page 617 of your textbook, and the title of this section is the Integral Test and P-Series. Remember that we are discussing series in this chapter, infinite series in particular, and up through section 9.6 we're going to be curious about whether or not they converge or diverge. We're going to learn a series of tests which will help us determine whether they converge or diverge. We will also learn categories of series which will allow us to make decisions about their convergence or divergence. And so we're in the process of learning these things in section 9.3. For this section, we will look at one test to determine whether or not a series converges or diverges, and one category of series called P-series. We'll start with the integral test, and this is one of the tests which can be used for series with positive terms. It's called the integral test. It says, let your general term be a function f of n. Then, if f is positive, continuous, and decreasing, you are allowed to use the integral test, and what we discover is that the sum of this series and the integral of this function from 1 to infinity either both converge or both diverge. We say that the series and the integral go together. They both converge or both diverge. Now, once you've met the three conditions for using the integral test, essentially you're taking the integral from 1 to infinity and you're seeing if the integral converges or diverges, and that will tell you then if the series converges or diverges. So let's see how this test works. In example 1, we're going to apply the integral test to the series n over n squared plus 1 from 1 to infinity. Now, we're going to let this general term, n over n squared plus 1, be a function, and I'll call it f of n, is equal to n over n squared plus 1. We're going to see if for n greater than or equal to 1 that these terms or this function is positive, if it is continuous, and if it is decreasing. And if these three conditions are met, we'll be allowed to use the integral test. We'll integrate this function from 1 to infinity, see if the integral converges, and that will tell us if the series converges. First of all, notice that for n greater than or equal to 1, the numerator will always be positive, 1 or higher. The denominator is always going to be positive also because you're squaring a number and adding 1. So the terms, at least for n greater than or equal to 1, will all be positive. The function is positive as well. Then for continuity, we look to see if there are any asymptotes. In this case, there is no place where the denominator equals 0, so this function is continuous. To determine whether or not it's decreasing, we're going to need to look at the first derivative. So f prime of n is equal to, using the quotient rule, the denominator, n squared plus 1, times the derivative of the numerator, which is 1, then minus the numerator times the derivative of the denominator 2n, all over the denominator squared. Simplifying this numerator gives me n squared plus 1 minus 2n squared, which simplifies to negative n squared plus 1 all over n squared plus 1 quantity squared. I didn't write the denominator there, but you know it goes there. Now let's decide whether or not this first derivative will be decreasing from 1 on. Well, if we put 1 in here, you can see that we end up with 0 in the numerator, but everything larger than 1 gives us a negative term because it's going to be a negative numerator over a positive denominator. So this does meet the condition of decreasing. So now that we see that the three conditions are met to use the integral test, we're going to take the integral from 1 to infinity of n over n squared plus 1 dn in this case. Now this is setting itself up to be a natural log integral because if we say that u is equal to n squared plus 1, we can see that du is 2n dn. So if I put the 2 here and compensate by putting 1/2 on the outside of the integral, this ends up being 1/2 the natural log of n squared plus 1 from 1 to infinity. Since this is an improper integral, I should have set this up as a limit, as you know, and shame on me for not doing that. So let me go over here and show you what that would look like. It would end up being the limit as n approaches infinity of the integral from 1 to n. I guess I should have used a different variable. From 1 to b of, I'll go ahead and put the coefficient that I added, 2n over n squared plus 1 dn. Now, as we are going to evaluate this, we'll say b to infinity, as b approaches infinity, from 1 to b. And now, let's go ahead and see what ends up happening. For our first term, as we put b in for n, we end up with the limit, as b approaches infinity, of 1/2 the natural log of b squared plus 1, and then minus, we won't need the limit for plugging in the lower end point of integration here, we end up with minus 1/2 the natural log of 1 squared plus 1, which is just 2. I guess I don't need the absolute value bars there. We will take them away, natural log of 2. However, as exciting as it was to get something that is an actual number here, plugging infinity in here gives us a divergent limit, which is a divergent integral, which takes us back to the fact that we were wondering whether or not this series converges or diverges. And since the integral diverges, the series diverges. And that's how you use the integral test. Let's do another example using the integral test. In this case, we have the function 1 over n squared plus 1. I'll write this as f of n is equal to 1 over n squared plus 1. Now, the three conditions that need to be met, of course, will this function be positive, continuous, and decreasing when n is greater than or equal to 1. Notice that, of course, this function is always positive because whatever number we put in for n, we're squaring it and adding 1. That makes your denominator positive, and of course 1 is positive. So it does meet the condition of continuously being positive. Now let's see if the function's continuous. We would look at the denominator to see if there are any asymptotes, and that denominator will never be 0, no asymptotes, so this is a continuous function. To determine whether or not it is decreasing, we're going to have to take the derivative. So f prime of n is going to be, let's actually rewrite this function as n squared plus 1 to the negative 1 power. That will be negative n squared plus 1 to the negative 2 times the derivative of the inner function, which is 2n. So we end up with negative 2n over the quantity n squared plus 1 quantity squared. Notice that for n greater than or equal to 1, the numerator will always be negative, but the denominator will always be positive. So this is decreasing continuously for n greater than or equal to 1. You can see that we have a graph here, and it does meet the criteria, all positive values, continuous, and decreasing at least for n greater than or equal to 1. Since those three conditions have been met, we can use the integral test here. That means I'm going to take the integral from 1 to infinity of the original function, which is 1 over n squared plus 1 dn, and let's immediately change this to a limit because we have an improper integral here. The limit as b approaches infinity from 1 to b of 1 over n squared plus 1 dn. Now you can see that this is just the arctan integrand pattern, and so the integral of 1 over n squared plus 1 is going to be, let's go ahead and put limit as b approaches infinity of arctan of n, and then we're integrating that from 1 to b. This is going to give us the limit as b approaches infinity of arctan b, minus, and we don't need the limit for this next piece, we can just say minus the arctan of 1. Now let's plug infinity in for b. Interestingly enough, arctan infinity means the tangent of what angle equals infinity. If you recall, the tangent graph has vertical asymptotes all through it, so we do have values where tangent is infinity. So this is going to be pi over 2, but let me finish this. Minus arctan of 1. Again, we're wondering where tangent is equal to 1. So it turns out that, since I'm kind of running out of room down here, I'm going to change colors. This is pi over 2 minus pi over 4, which is where tangent is equal to 1. So we end up with pi over 4. Notice that is not divergent. It is a value. We were able to actually get a value for this integral, which means that our series converges. All we had to do was show that the integral converged to something, and we showed that it converged to pi over 4. Therefore, now we know that our series converges. It does not mean that the sum of the series is pi over 4. All we know is that it converges. Okay, we discussed the integral test, and that was a test for convergence or divergence. Of course, it has to meet certain conditions, but if it does, that is one way to determine whether or not a series is convergent or divergent. Now we're going to move to the category of series called p-series. The following type of series has a simple test for convergence or divergence. This series is called a p-series and has this form: the sum from 1 to infinity of the general term 1 over n to the p. Notice that n is changing, and that is the base of the exponential function. So each term is 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to the p. The exponent doesn't change as it does in the geometric series. The base changes here in the p series. When p equals 1, the harmonic series is formed. So the harmonic series looks like this: 1 over n from 1 to infinity. Because now if p is 1, we have 1 over 1 to the 1, which is 1, 1 over 2 to the 1, which is 1/2, plus 1 over 3 to the 1, which is 1/3, etc. The harmonic series, of course, is a very important series in nature, in creation. A general harmonic series is of the form 1 over an plus b, and in music, strings of the same material, diameter, and tension, whose lengths form a harmonic series, produce harmonic tones. So this is a very important series to know, and it is a specific type of p-series. Now that we know that there is such a series with this characteristic, let's determine how to see if it converges or diverges. It turns out that if p is greater than 1, then the series converges. If p is between 0 and 1, it diverges. If it's equal to 1, it diverges. Therefore, the harmonic series where p was equal to 1 diverges. So this is a very simple way to determine convergence or divergence, but of course it has to be this specific category of series. It has to be a p-series. So if you look at your function and it falls into this category of series 1 over n to the p, then you'll easily be able to tell if it converges or diverges. Notice that we don't say when p is negative, because of course if the exponent was negative, that would put the term into the numerator, which would not be the form that we're looking for. We're looking for 1 over a base time to the exponent, to a certain exponent. So let's apply the p-series test for convergence. The harmonic series, as we know, p is equal to 1 in the harmonic series, if you recall from the previous slide. And as you can see, if p is 1, or between 0 and 1, the series diverges. So the harmonic series, even though it seems as though it should converge, it doesn't. Let's just take a look at it for a moment. We're going from n to equals 1 to infinity of 1 over n, or n to the 1, where p is equal to 1. These terms are 1 plus 1/2 plus 1/3 plus 1/4, etc. And it seems as though, since these terms are getting smaller and smaller and smaller, that maybe it will converge, but it doesn't. And so we just need to make a note of this. This will definitely be a question on the AP exam somewhere, whether it's a multiple choice question or part of a free response question. But take note of the harmonic series, very important, and the fact that it diverges because p is equal to 1. Now let's look at a p-series with p is equal to 2, just to see what that looks like. It would be n is equal to 1 to infinity of 1 over n squared. So as n is changing, that's going to be 1 over 1 squared, which is 1. Plus 1 over 2 squared, plus 1 over 3 squared, etc. And that, of course, is 1 plus 1/4 plus 1/9. And I'm just showing you what this looks like for fun. We already know that since p is equal to 2, based on the rule that we have been given, since this is a p-series and p is greater than 1, we know that this series converges. So hopefully all of the questions that you ever have about convergence or divergence are p-series, because it is an easy test to administer, and that's it. Let's look at the last example. In example 4, we're going to use the integral test to test for convergence for this general term, 1 over n natural log of n. And notice that we're starting from 2 to positive infinity, and this is because, as we know, the natural log of the natural log of 1 is 0. So we can't start at 1, since that would put 0 in the denominator of this term. Therefore, we're avoiding that problem by starting at 2. Now, we do have some conditions to meet. This needs to be a positive, continuous, and decreasing function for n greater than or equal to 2 in this case. Let's go ahead and write this as a function. F of n is equal to 1 over n natural log of n. Now, I notice that the book actually changes this to x. F of x is equal to 1 over x natural log of x. That's fine. It doesn't really matter as long as you understand what's going on. So now let's see if this function is going to be positive for n greater than or equal to 2. Well, the natural log of 2 or greater is a positive quantity. Obviously, 2 or greater is positive. 1 over a positive number gives us a positive function for n greater than or equal to 2. How about continuity? The only place where this would have been a continuity issue is if n was equal to 0 or n was equal to 1. That would put a 0 in the denominator in either of these cases. But since we're starting with 2 and larger, no need to worry about discontinuity in this function as well. To determine whether or not it's decreasing, I will need to take the derivative. So I'm going to rewrite this function as n natural log of n to the negative 1. That means the derivative will be negative 1 times n natural log of n to the negative 2, and then I have to take the derivative of the inner function, which will involve the product rule. So this is going to be times n times the derivative of natural log of n, which is 1 over n, plus the natural log of n times the derivative of n, which is 1. This simplifies to the negative 1 times n over 1 is 1 plus natural log of n, that's my numerator, over the quantity n natural log of n squared. Now we need to know, is this guy decreasing for n greater than 2? Well, of course, inside parentheses here, we're going to have a positive number because natural log of 2 or larger is positive, and adding 1 makes it positive. but the negative means the numerator will always be negative, and then the denominator is always positive because it's squared. Therefore, this function is decreasing for n greater than or equal to 2. Now that we've met the condition for using the integral test, we actually have to use it. It's a lot of work just to see if we can use this test, isn't it? That's what we do, boys and girls. So we're going to say from 2 to infinity of 1 over n natural log of n dn. And because this is an improper integral, we're going to change that to the limit as b approaches infinity from 2 to b of 1 over n natural log of n dn. Now you might be able to see that this dn and this 1 over n part is the du of natural log. So if I go off to the side here and say, let's let u equal natural log of n, the du is 1 over n dn. So this part and this part is the du of the u, which is natural log, which gives us this interesting integral. It's actually going to be du over u, where u is natural log of n. The integral then will be the natural log of u. Since this is just following this little template here, since this is natural log of u and our u is natural log of n, it ends up being the natural log of u. So back to green, and we're going to take then the limit as b approaches infinity of the natural log of n from 2 to b. Now, when we plug in b, we're still going to have to use the limit designation for the first term, and that means we're going to have the natural log of b, then minus, again, we don't need the limit for plugging in 2. We can just say minus the natural log of 2. However, we have a problem here. Plugging b, infinity in for b gives us infinity, and then the natural log of infinity is also infinity. So we have discovered that this integral diverges, which means, of course, back to the original series, who can even remember that this is where we started? We can, boys and girls. It also diverges, and that is, once again, the integral test in action. Now, this finishes up our lecture for today, but I wanted to give you a look at a summary of tests for series. This should be on page 644 of your textbook. And it just sort of quantifies what we will be going through in this chapter. What we have done so far, we have discussed the one test that we have for divergence, the nth term test for divergence. We have gone over that. These 4 things here are categories of series. So remember that we have 2 things that we look at. Categories of series which follow certain rules for convergence and divergence, and then we have just tests for divergence. So these are actually tests for convergence, convergence. We only have 1 test for divergence, and convergence, keep spelling. Okay, whatever, that's convergence. 1 test for divergence. We have 4 categories of series, and then we have 5 tests for convergence. Well, notice what we've done so far. We have discussed the nth term test for divergence. We have explored the geometric series, the telescoping series, and the p-series. We have also looked at the integral test. So just sort of taking stock as of now, this is where we are. In the next lecture, we're going to look at these 2 tests, these 2 comparison tests, and then we'll come back and pick up alternating series and the root and ratio tests. So just to give you an idea of where we are. And then I'm going to end this lecture with some classic asymptote humor. That's it for this lecture, boys and girls. God bless you.